Extreme Physics.
Alright, this is the 2019 AP Physics C exam, parts 1 through 3. This was called Set 2. They posted 2 exams for that year, and this was called Set 2. Alright, let's take a look at the first problem. Blocks of mass M and 2M are connected by a light string. Alright, light string. That means no mass. We don't have to worry about the mass of the string. The string has no inertia. The string has no weight. The big thing is the string has no inertia. But anyways, a light string placed on a frictionless incline. All right, that's important. No friction on the incline. Makes an angle theta with the horizontal as shown in figure 1 above. Another light string. Okay, no inertia, no weight. Connecting block of mass M to hanging sphere capital M. Passes over a pulley of negligible mass. No rotational inertia. All right, so that means that T2, the tension on T2, is the same as the tension on capital M, the sphere. Since there is no rotational inertia, it takes no net torque to rotate that thing, so the tension on both sides of the pulley are going to be the same. And negligible friction. All right, so there's no friction. So again, the tension T2 is going to equal the tension that is on the sphere, the hanging sphere. The entire system is initially at rest and in equilibrium. All right, well, yeah, okay, it's at rest, so it's in equilibrium, sure. I don't know how you can be at rest and not be in equilibrium, but whatever. On the dots below that represent the block mass M and sphere mass capital M, draw and label the forces, not the components, that act on each of the objects shown. Each force must be represented by a distinct arrow starting on and pointing away from the dot. There's a normal force. The surface is applying a force perpendicular to the surface, which is the normal force. It's called normal because normal means perpendicular. And all right, we also had T2. This is M, right? This is M. We had T2 was pulling up, and we had the weight, which would be mg down. And there was no friction, but we also had T1 like that. Okay, these two had to be parallel to the dotted line. This one had to be perpendicular, and this one had to be straight down. Make sure straight down towards the bottom of the page. All right. Hopefully that wasn't too hard. And M just had, what was that, T2? T2 was up, and capital MG was down. Those should be equal in magnitude. This isn't quite right. Because this component has to equal that, so that should have been probably a little less. But I don't know if they were looking at the magnitudes, because the component of this one down plus that should equal that, because it's at rest. So could probably lower this a little bit too. Something like that. All right. There we go. So we got our forces. The block, we had 2 tension forces, a normal and a weight force, and this one we had tension 2 and the weight. Derive an expression for the magnitude of each of the following. If you need to draw anything other than what you have in part A to assist in your solution, use the space below. All right. I will. All right, I'm going to draw a free body diagram. Apart from that thing on there, don't use the thing on there. Draw your no free body diagram. Give yourself a coordinate system. And I had mg down. And this was theta right here. And we had the normal force. And we had... Now, what are we trying to find? T2. Now, to make my life easier, what I'm going to do is... Because T2 is doing a couple of things, right? We got our 2 blocks here. and we had T2, and this thing is at rest. And what T2 is pulling on block M, but block M is pulling on T1, which is pulling on 2M. And T2 is essentially kind of pulling, it's not directly pulling on this, but it indirectly is. So I'm actually, since these would move together, I'm actually going to treat this like I have one object. T2 is pulling on one object of mass 3m, right? Because as far as T2 is concerned, it doesn't know it's two blocks. It's just connected to this thing, and it's pulling back with a force as if it was one thing with a mass of 3m. So I'm going to do that because otherwise I'm going to have interacting diagrams and stuff like that. It's going to slow me down, and there's no need for that. I'm going to simplify this, and I'm just going to say my object of interest is this, right? So if that's my object of interest, now T2 is the only tension force on my object of interest. So I'm going to have my object of interest, so I'm going to treat it like it's this is one thing of 3m. So in this case, this mass on this thing is 3m, right? So it's 3m. We got to think it's 3m, and there's a tension T2 pulling on this thing of mass 3m because our object of interest is going to be both those things. So, and we just want to know what T2 is. Well, let's apply Newton's second law. In case this is kind of like first law, but second law with the acceleration equals 0. Sum of the forces equal mass times acceleration. I always state the physics. All right. So in this case, sum of the forces in the x equal mass times acceleration x. I tilted my axis. Let's remind ourselves why we tilt our axis. In this case, I'm going to tilt my axis because if there's going to be an acceleration, I want it to be along one axis, right? In this case, if I tilt it, there won't be an acceleration in this particular portion of the problem. But anyways, the acceleration is 0 because it's at rest. So we have T2 minus 3mg sine of theta, right? We want this component. We want the component down there in the x direction, which is going to be the total weight times the sine of theta equals 0. All right. So it looks like T2 equals 3mg sine of theta. And that was quite easy by just choosing my object of interest as a single object with one tension force rather than circling this in case we'd have two tension forces, and then we'd have to analyze that to figure out what that tension force is and solve simultaneous equations. And we don't want to bother with that because it's really unnecessary and it would be very time consuming, certainly if you're taking an exam. All right. So I guess BI says that T2 is 3mg sine of theta. All right, might need that later. I don't know. All right, now find the mass m for which the system remains in equilibrium. Oh, I got to make sure. Express your answer in terms of m theta and physical constants. M theta, physical constants, and 3 is a constant, I think. All right. So I'm going to treat this like we have a single object of 3 little m, right? I know they're attached by strings, but if we don't care about what the tension force is on the 2m block, T1, if we don't care about that, let's eliminate it. Let's choose our object of interest as both of them together, right? So we'll do that. This is going to remain at rest. So let's take a look at M. Boom. Circle object of interest. What do we got? We got Y. We have X. Downward we have capital MG. Upward we have what they call T2. They should be equal. They're about equal, I guess. The way I drew them, make sure you kind of drew them about right. All right, I got myself a nice free body diagram. Let's state the physics. Sum of the forces equal mass times acceleration. In this case, the sum of the forces in the Y equals 0. T2 minus capital MG equals 0. T2 equals mg. So T2 equals mg, but T2 also equals 3 mg sine of theta. So let's take our answer from here and plug it into here. And, we had for earlier, we said T2 equals 3 mg sine of theta. So let's just take this, plug it into there, and we end up with 3 little mg sine of theta equals mg. G's can go away. So I guess m equals 3m sine of theta. All right, I guess that's m. Certainly the units work out. Now suppose that mass m is large enough to descend and the sphere reaches the floor before the blocks reach the pulley. All right. Answer the following for the moment immediately after the sphere reaches the floor. All right. So this thing's going to slide down like this, and this is going to hit the floor before this hits the pulley. We may or may not be doing this. So for now, let's see what they ask us. We got 2 blocks. Does the tension T1 increase, decrease to a non-zero value, decrease to 0, or stay the same? So this thing's going to come down, it's going to hit, right? And so when it hits, T2 is going to become less. What happens to T1? Let's say this was an object of 3m. Right? And you got the pulley, and you're going like this. And you're going up, and you have a velocity. Now, we don't know whether it's accelerating or going at constant velocity. They didn't say. It's just moving up. And then all of a sudden, it stops. So, at the very least, if this is going at constant velocity, if it's moving like that, so this hits, and we know if it's constant velocity that our tension force T2 on our block 3m has to have a component that's about that long, which is 3 mg sine of theta. And these two must be equal, let's say, for the sake of argument, because the minimum weight of this for it to be falling down would be that it was going at constant velocity. It might be accelerating, in which case it makes it a little easier to understand, but let's take the worst case scenario. So anyways, it's going like this, then this hits the floor, right? So we've lost the weight of this thing. So what happens to T2? It plummets. It plummets, right? It plummets. In fact, it's going to go to 0, right? So now we have a net force on this system down. This whole thing wants to accelerate down. Well, let's take a look at the 2 blocks. Well, we had block 2M like this, and it had a tension T1, Y, X, and this was 2mg. This is theta. This is a normal force on 2. And then we also had this one, which had T2, and we had mg, and we had theta, and we had our normal force, normal 1, I will call it, y and x. And we also had T1 acting on that, T1. And these were Newton's third law pairs. These two T1s were the same. Now, as soon as we drop this to 0, because it hit the ground, this is going to accelerate this way. This is going to accelerate down 2. What's going to happen to T1? What's going to happen to T1? Well, it's kind of hard to see what's going to happen to T1 here, right? Because we don't know what's going on. But here, it's a little easier to see what's going to happen to T1. In order for this to accelerate down, and it has to, the whole system's going to accelerate down because it lost this, T1 has to drop. T1 has to drop. And, okay, so that's a decrease. Now, is it going to decrease to 0, or a non-zero value? Are they going to be pulling on each other? Well, let's take a look at this thing. Let's take a look at this thing. If I get rid of that, because this isn't pulling down anymore because it hit the ground so it no longer has the weight pulling down on it. What this is going to do is, if we take a look at this object, 3 mg, we got a normal force and nothing up. The sum of the forces in the x equals mass times acceleration in the x. So we end up with downward we have negative 3 mg sine of theta equals 3 ma. Right? And the 3's go away too. So the acceleration equals minus g sine of theta. Right? That's going to be true of the system. The system is going to accelerate down at negative g sine of theta. Well, that's just the acceleration of anything on a frictionless ramp is g sine of theta. You're going to get that answer no matter what this thing is. So these left to their own devices would accelerate at that rate. They're accelerating at the same rate. The tension for T1 will be 0, right? The only way you could have a tension of non-zero is if this one wanted to accelerate less than that one, right? So T1 is going to be decreased to 0. There's not going to be any more tension between T1 and T2 because they're going to be accelerating at the same rate. Decrease to 0. Is the velocity of the block of mass m up the ramp, down the ramp, or 0? Well, it was going up the ramp, and all of a sudden we cut that, so it now has a downward acceleration. But because it had inertia, it's still going to have an upward velocity. It's still going to go up the ramp for a little bit. It's going to slow down and go down the ramp eventually. But initially, it's going to be going up the ramp. It does have a downward acceleration. It was already moving up the ramp. It's going to continue to move up the ramp because of its inertia. A body in motion stays in motion. There was an unbalanced force, so it's accelerating down. It's going to slow down, stop, and then come back. Is the acceleration of the block mass m up, down the ramp, or 0? It's down the ramp. M is down the ramp. There are no upward forces up the ramp. There's only downward forces. So that is down the ramp. The acceleration is down the ramp. Consider the initial setup of figure 1. All right? It's been officially considered. Now suppose that the surface of the incline is rough and the coefficient of static friction between the blocks and the incline is mu s. All right, so we have friction, mu s. I'll write that there. There's static friction. Derive an expression for the minimum possible value of m that will keep the blocks from moving down the incline. Express your answer in terms of mu s, m, and theta as appropriate. Treat this as an object of mass 3m. Just to speed things along here, because, you know, if we're on the exam, we don't really have a heck of a lot of time. Not a good drawing, but anyway. Here we go, capital M. We have mu static here. All right, so it wants to go down the incline. Now, there are a number of values of m that would keep this at rest, but we want the minimum value of m, so these are kind of wanting to slide down the ramp, but this is just enough to prevent that. That's an important idea, that they gave us just enough of that, because that tells us we're going to use maximum static friction when we look at this thing. So I got my object of interest again. Different free body diagram this time, though, because we have friction. So up the ramp, we have tension. I keep forgetting, that's T2, right? T2. And down the ramp, we have something kind of like that. And that would be 3m. And this would be theta. That tells us that friction is this way, right? There's our friction, and it is static. And it is a maximum static. It is a maximum, because they want the minimum value here. So it's got to be just on the verge of sliding down. That means that our static friction is maximized, and we're not moving. So if I circle this object of interest, we know that we got mg down, and we got T2 up, and here's our y, there's our x, and we know that these act as if they are Newton's third law pairs. They clearly aren't because they're not in opposite directions, but we can blame the pulley for that. The magnitudes are certainly the same. So here, if we just take a look at some of the forces in the y equals 0, so T2 minus mg equals 0, so the tension of 2 equals mg. So we know what that is. Let's take a look at this one, and we got some of the forces in the x direction equals 0 because it's at rest. So what do we got? We got T2 plus friction static max minus 3 mg, that should be a g, 3 mg sine of theta equals 0, right? We want the component, which is that way. I drew that too small. It should have been bigger compared to this stuff. But I'm not going to fix that right now. We're looking for what must that be. So I'm going to plug this in, actually. For T2, I'm going to plug T2 in right there. Mu static. Normal, because this is static max, it's just mu static normal. Minus 3 mg sine of theta equals 0. All right, so we just need the normal force. And draw the normal force. I missed my normal force. Missed that. You need the normal force. And the surface is pushing up on it. All right. So the normal force is going to equal the component of the force in the y direction. I'm going to do that right here. Don't have a lot of room. So I'm going to say the sum of the forces in the y direction equals 0. So normal minus 3 mg cosine of theta equals 0. So the normal force equals 3 mg cosine of theta. Be careful on that. I notice a lot of times students will just automatically say, oh, the normal force equals the weight. Well, no, it doesn't. Not in this case. So in this case, normal force equals that. We're going to, is 3 mg sine of theta, cosine of theta. Put that in there. So we ended up with mg plus mu static 3 mg cosine of theta minus 3 mg sine of theta equals 0. It looks like the g's go away. All right, so I just need to solve that for m. M equals 3m sine of theta minus mu s 3m cosine of theta. I guess we could say 3m sine of theta minus mu s cosine of theta. Let's see the units work out. The string connecting block mass m and sphere mass m then breaks. It breaks. And the blocks begin to move from rest down the incline. The lower block starts at distance d from the bottom incline as shown in figure 1. The coefficient of kinetic friction between the blocks and the incline is mu k. Derive an expression for the speed of the blocks when the lower block reaches the bottom of the incline. Express your answer in terms of md mu k and theta. I should make sure I did my thing right in terms of this. Express your, for d, express your answer in terms of m, mu, and theta in physical yes, okay, so we're good. All right, so this whole thing's going to move a distance d, well, I know how fast it's going when it gets to the bottom. Now, I know most people would probably just find the acceleration of this thing and use kinematics, which is certainly fine. You can use the kinematics equations because the forces are constant. So therefore, it's a constant acceleration. And I would just look at this as an object of 3m and do that. But I'm going to use a different technique. I'm going to actually use conservation of energy. That's good practice. Let's take a look at that using conservation of energy. Because we have a system that's going to drop. These things are both going to drop by the same amount. So again, I'm going to just treat it as one block. So if we had this block of 3m, and it traveled a distance d. But we really want to know what h is. We want to know how far it fell, because we want to know about its loss of gravitational potential energy. All right, well, that's not too hard to figure out, though, because h is just h is just d sine of theta. I'll say the gravitational potential energy is 0 here. So I would say the energy at, and I will call this position 0. And when it gets to the bottom, it's at 1. I'm not going to redraw it just because I'm running out of board space here. I need a bigger board. But the energy at 0 at the top equals the energy at 1 at the bottom. All right. Now, in this case, mechanical energy, of course, is not conserved because there's friction. Friction's not a conservative force. There's no potential energy associated with it. It is a lossy force, non-conservative. All right. So anyways, so we start off with here, and the question is, does it have height? Yes, it does. So we end up with the gravitational potential energy at 0. Is it moving? No. Is there work being done? No. Well, I mean, no external work, because we're going to include the Earth in the system. The Earth is pulling on it, and it's pulling on the Earth, but that's internal, and we've taken that into account with our gravitational potential energy. It's not moving. So I guess that's all we have on this side. Now, on this side, does it have height? No, because I defined height 0 is 0 there. All right, doesn't have height. Now, does it have speed? Sure. Yeah, it does. Is it rotating? No, it's not rotating. It's a block. And are there any thermal losses? Yeah, there is. There is delta E thermal, right? So it's going to warm up a little bit. The ramp's going to warm up a little bit, get a little warmer, more thermal energy, and so is the block, right? And all right. So this is just going to be I'll say 3M. 3mg h, right? This h equals 1/2 3m v1 squared, and that's what we want to know. We're going to know what v1 is, plus E thermal. And we can think of that as kind of like the work that friction did. It's the force of friction, in this case kinetic friction, times d, right? Friction acted this way, and exactly opposite the direction of the displacement. So it's just the force times the displacement, friction times the displacement. All right, so let's expand this a little bit. 3mg d sine theta equals 3/2 m v1 squared plus mu kinetic normal d. All right, so we got 3mg d sine of theta equals 3/2 m v1 squared plus mu k. What was our normal force? Keep in mind, it is not the weight in this case. We had 3mg down, theta n. Sum of the forces in the y equals 0. Normal minus 3mg cosine of theta equals 0. N equals 3mg cosine of theta. All right. So what do we have? We had 3mg cosine of theta d. Well, m's can go away. I'll go in a different color. It's so messy. Let's go with red. Maybe you can see what's going on. M's go away. Get rid of the 3's. It's about all I can get rid of. All right, what do we end up with? We ended up with GD sine of theta minus mu k g cosine of theta d equals v1 squared. I'll multiply the whole thing by 2. Are my units working? Meters per second squared times per second squared. meters squared per second squared. Square that. Yeah, that's good. Yeah, units are working. Might be right. Might be right. This could very well be correct. Is that right? Is that right? Did I miss anything? 2GD, 2GD. I think that's it. I think that's it. All right. So that's V1. Now again, you certainly could have just calculated the acceleration of this easily enough, and then use kinematics. But here, good practice, conservation of energy. This is the 2019 question 2 from set 2. A toy rocket of mass 0.5 kilogram. Accelerates from rest. On the ground is launched upward, experiencing a vertical net force. All right, it's accelerating upward. The rocket's upward acceleration, A, for 6 seconds is given by A equals capital K minus LT squared. I smell calculus. Where K is 9 meters per second squared. So this is only from T equals 0 to 6 seconds. At 6 seconds, the fuel exhausted, and it's under the sole influence of gravity. Acceleration equals negative G for T greater than 6 seconds. Assume air resistance and the rocket's change in mass are negligible. All right. No. All right. Calculate the magnitude of the net impulse exerted on the rocket during this time. All right. So let's see what we got. We got impulse. Now, impulse, of course, it's a vector, and it's the integral of F. It's F dt, right? And that equals a change in momentum, right? So sometimes if they ask for that, we're just going to figure that out. But in this case, they gave us acceleration. So we know through Newton's second law, if we know the acceleration, we can get the net force or the net force of the acceleration as long as we know mass, because we got a relationship, right? So we can get the net force from the acceleration. So we're going to do that. We know that acceleration equals net force divided by mass, right? So therefore, net force equals mass times acceleration, right? Either way you want to look at that, that's cool. So all we need to do is take this. So therefore, in this case, it's just m times k minus LT squared. That is the net force. I'll just put F net. The magnitude of the impulse, and it's going to be in the direction, it's going to be upward impulse. Let's just calculate the magnitude. Right now is going to be m times k minus LT squared dt as time goes from 0 to, so we want it for the whole 6 seconds. So I guess I'll break it into two integrals. We'll go from 0 to 6, and we got m k dt minus integral from 0 to 6 m LT squared dt. All right, and these are just constants, and that's constant. And, all right. So this equals mk integral of dt is just t, 0, 6. Minus, bring out the m and the l. And we had t squared dt, which of course is just going to be t cubed over 3, 6, 0, something like that. Of course, you can bring the 3 out. All right, so what do we got? 6mk minus m over 3 L 6 cubed. All right, we have numbers for those, I guess. I got these numbers. Hey, we have these numbers. All right, 6 times... Well, I'm going to take the mass out because I don't like numbers, and the only thing I like less than numbers is repeating calculations on numbers. So I'm going to take the m out, I think. I got a 6 I could take out, too. All right, I'm going to bring out a 6 and an m. All right, so 6, I'll bring out one of these 6s, and that one 6, and then m is 0.05 kilograms. All right, so I brought that. I got 6m out. K is 9 meters per second squared minus m over 3. We already got the m. I already took the m out. And so we got L 0.25 meters per second to the 4th over 3 times 6 squared, right? We lost one of our 6's when we factored it out. That's seconds. 18 should be Newton seconds. Let's see if it is. I've been a little sloppy with my units here. Let's see if it actually is. What do we got? So a Newton second. Let's review. A Newton, which is mass times acceleration, F equals mass times acceleration, is a kilogram meter per second squared. So this would be kilogram meter per second squared times seconds, or kilogram meters per second. All right. So we got kilogram times meters per second. That's good here. So this better be meters per second squared. Meters per second to the 4th times second squared is meters per second squared. The units work out just fine. So the answer might just be fine. The answer might be fine. Might be. All right? It's not obviously wrong. That's all I can say. Upward. Let's see. Did they just say the magnitude? What did they say? What was the question? Calculate the magnitude. Well, anyways, I went above and beyond. The Call of Duty, I actually gave the direction to our vector. You know, we found the impulse. I hope we need the change of momentum here, because otherwise it's like, what's the point? What's the point of finding the impulse if we don't need the change of momentum? Calculate the speed of the rocket after 6... Oh! Hey. We're going to use change of momentum. We're going to use impulse equals change of momentum. That's what we're going to do. Impulse causes a change in momentum. Calculate the speed of the rocket after 6 seconds. All right, well, that was impulse after 6 seconds, 18 Newton seconds. So, impulse causes a change in momentum. That's a reworking of Newton's second law. All right, we should derive that. That's easy to derive. That is a restatement of Newton's second law. Of course, they're vectors. All right, so impulse equals P1 minus P0. I should have a diagram here. I should have a diagram of what's happening here in this problem. We got a rocket. I'm going to set up a coordinate system. We got a rocket. It's got to take off from the ground. That's times 0. And it's going to go up to some height. And there's 1. And in this case, T1 equals 6 seconds. T0 equals 0. It's going to run out of fuel. And at some point, it's going to stop in this problem. So at this point, this is when the fuel runs out too. Fuel runs out. It's going to coast. And I'll say V2 equals 0. That's when it's going to stop. And then it's going to fall back down. There's an impulse from here to here. This is the impulse from 0 to 1. I'll do that. That's the impulse from 0 to 1. And equals the momentum of change of momentum from 0 to 1, which is momentum 1 minus momentum 0. But momentum 0 is 0 because it wasn't moving. It had no velocity at that point. So, all right. So impulse from 0 to 1 equals mv1. And that's what we want, right? We want the speed of the rocket at 6 seconds, which is 1. So V1 equals impulse from 0 to 1 divided by m, which is 18 Newton seconds divided by the mass, which is half a kilogram, which I guess is 36 meters per second. All right, do my units work out here? Now, probably more appropriate units, since we're for change of momentum, would be 18 kilogram meters per second. Units for momentum divided by that kilograms. The kilograms go and we end up in meters per second. All right. Calculate the kinetic energy of the rocket. All right. Now it's just getting tedious. It started off interesting, now it's just getting tedious. So the kinetic energy at position 1 is 1/2 mv1 squared. All right. That's 1/2 of the mass, which is half a kilogram, times 36 meters per second. The whole quantity squared. 324 joules. That's the kinetic energy at 1. Calculate the change in gravitational potential energy of the rock Earth system from t equals 0 to t equals 6 seconds. All right, so I guess we're going to figure out how high it went. To find out how high it went, this is a non-constant acceleration. So we can't use our kinematics equation. Don't even try that. That's a non-constant acceleration. You see that there? The acceleration is going down. It starts off at 9 meters per second squared and then slowly decreases till it gets to 6 seconds. It's 6 seconds. It's 36 times 0. The acceleration 0 at 6 seconds. So that's a non-constant acceleration. So don't even think about using the kinematics equations. All right, we're going to have to use calculus. We're going to use kinematics. We're just not going to use the kinematics equations. Those are the equations that are used under the conditions of constant acceleration. This is a non-constant acceleration. So velocity equals, change in velocity, equals integral of a dt. In this case, the initial velocity is 0. So this would just be v, because it's v minus v0, but that 0 equals integral of k minus lt squared dt. Really, we're looking for v of t. We're looking for a function, because we want to get we really want a position function to figure out how high it went. But anyways, we're just going to go from 0 to t. So let's just come up with our function from 0 to t. We end up with, I'm going to break this integral into 2 pieces. So we're going to go from 0 to t, k dt minus 0 to t lt squared dt. We're going to do that. And then I'm going to go one step over. And so that is just the integral of dt, because k can be pulled out. And that's k times t from 0 to t minus, again, I'll bring the L out. We got t cubed over 3 from 0 to t. All right, so we'll do something like that. And then we'll go like this. What do we got? kt minus L over 3 t cubed. All right, so there's our velocity function, v of t. And our units working? Yep, we got k is meters per second squared times seconds, meters per second. L is meter per second fourth. Yep, all right. So now we want our position function. We know delta y is going to integral of vy dt. You know, as you go from, we go definite integral here, 0 to 6 seconds. And, but it starts at position 0. So a delta y is just y at 6 seconds minus 0 equals integral of kt minus L over 3t cubed dt. as we go from 0 to 6 seconds. K over 2 t squared, 0, 6 seconds. Oh, but I'll run out of room. That's going to be t, so we're going to end up with L over 3 times 4 t to the 4th from 0 to 6 seconds. All right, I guess I got to plug some numbers in. K is 9 meters per second squared divided by 2 times, we're going to end up with 6 seconds squared, like that, minus L, which is 0.25 meters per second to the 4th, divided by 3 times 4, and those are just pure numbers, 6 seconds to the 4th. So we're definitely going to end up with meters here and meters here. All right, good, our units are working. So Y at 6 seconds, 135 meters. 135 meters is what it says. That's what the magic rectangle says. 135 meters high. Pretty high. I'll put that there. Y equals 135 meters. That's not what they asked, though. They wanted to know the gravitational potential energy. They wanted to know the change in gravitational potential energy. But I needed the height. Calculate the change in gravitational potential energy. Well, it started off at 0. And it's just going to be mgh. Change in gravitational potential energy is just going to be mg delta h, which is 0.5 kilograms times 9.8 newtons per kilogram times 135 meters. 660 joules. 662 joules. UG from 0 to 1 equals 662 joules. Oh no, that's not right. That's not D. That was I and I. That was I and I. Calculate the maximum height. I guess what it was. That's Y2. Y2 would be the maximum height. Right? The thing goes, it's accelerating up. It's accelerating tremendously upward, and then it runs out of fuel. But Newton's laws say that it's going to continue to move. The law of inertia says it's going to continue to move up. It's accelerating down. It's slowing down. It's eventually going to stop, and then it's going to start falling down. All right? So its maximum height is due to its inertia. It's going to continue going fast. It's going fast there. I forget. It's going 36 meters per second. When it runs out of fuel, it's not going to just stop. Then hit the brakes. It's going to keep sliding up. Gliding up. Not sliding. Gliding. Not sliding. Gliding. Calculate the maximum height reached by the rocket. We could just use kinematics. We could use kinematics. Right? We could also use conservation of energy. Because we have the speed and the height. Yeah, let's do that. Gravitational potential energy is 0 here. Mechanical energy is conserved at this part. All right, so the let's say the energy at 1 equals the energy at 2. In fact, mechanical energy is conserved between 1 and 2. It wasn't conserved between here and here because we had this thrust force. But in this case, it is. The only thing acting on is gravity. That's a conservative force. So is it moving? It sure is. It's going at 36 meters per second. That's pretty fast. Energy at 1 equals the energy at 2. So it is moving here. So we got K at 1. Does it have height? Sure does. Sure does. We're saying 0 here. So that's plus mu g UG1. No work being done between here and here. Now I know you can look at it in a certain sense, say that gravity's doing negative work, except that it's taken into account with our gravitational potential energy. So we've already taken that in. Gravity is internal to the system. We're including the Earth in the system in this case. We can tell because we're using gravitational potential energy. Kinetic energy at 1 is, or at 2 is 0. It has no kinetic energy. It does have gravitational potential energy. And there's no change in thermal energy because they said wind resistance and all that was negligible. So what do we have? We have 1/2 mv1 squared plus mgh1, which is y1. I'll call that y1. y1 equals mg y2. y2, that's a 2. All right, so we just need to solve for y2. Masses go away. It doesn't matter what the mass is. So we end up with v1 squared over 2 plus gy2 divided by g equals y2. So we end up with 36 meters per second, the quantity squared, divided by 2 plus 9.8 meters per second squared times. Wait a second. What? That's y1. That's y1. Not y2. The heck is that about? Y1 is 135 meters divided by 9.81 meters per second squared. That's y2. What do we got here? Meters squared per second squared divided. So we end up with meters with this. And meters, yeah. Okay, so the units are working out good. Maximum height. So we got some calculating to do. 201 meters. 201 meters. That's D. Y2 equals max height equals 201 meters. All right, then we end with a graph. Those graphs are always a good time. Let's take a look at our graph. All right, let's use our tools. The graphs are tricky. Most students find graphs tricky. So what do we have? We have a velocity versus time graph. So we got velocity and versus time. And you always want to use your tools. I'm going to put a reminder over here because it's usually kind of a good idea to look at slopes when you're doing a graph. So slope, in this case, equals dv dt, which is acceleration. All right, so the slope of this graph is going to be acceleration. Now, so the acceleration in the beginning is nonlinear, so we're going to have some sort of nonlinear thing. Now, this thing was speeding up the whole time, right? Well, for the first 6 seconds. So, like, if this is the first 6 seconds right here, it's going to start off with 9 meters per second squared. It keeps getting less and less and less. So it's going to start high, and then the slope's going to start rounding off until you get to, if you take a look at this, it's 6 seconds. What's the slope, right? Well, the acceleration at 6 seconds is 9 meters per second squared minus over 4. So it's a quarter times t squared, which is 36, which is 6 seconds squared, which is 36. What's 36 divided by 4? That's 9. So this is 9 minus 9, which is 0. So this is going to start off with a 9 meters per second squared slope and go to a 0 slope. So it's going to go something like that. Right? There's 6 seconds right there. So it should have gone like that and then levels off. And then all of a sudden, it becomes a constant acceleration because it's negative g. Right? So it's going to have to go something like that. And what do they want? They want, on the axis below, assume the upward direction to be positive. Sketch a graph of velocity versus time as a function of time to the time it reaches the ground again. All right? So it's going to go like this. But that's not the ground, right? That's not the ground. That's 2. That's when velocity is 0, right? And this is, the slope of this here is going to be, slope equals negative 9.8 meters per second squared. And it's not going to reach the ground until, right? Until what? It's got to start at the same position. And we know that delta y equals integral of v dt, right? So the area under this curve. So basically, when the area under this area equals you know, this area, when these areas are equal, whatever, that's when it's back to the ground, right? So, anyways, fun with graphs. Should look something like that, right? So, we had a changing acceleration till it got to 0 acceleration at 6 seconds because the function tells us that. And then we were at a straight line like that until it gets to, so where is T top? T top is right here. T top. That's T top. And this is, we could put that velocity, yeah, that was 36 meters per second. T top, it should have gone through because at the top the velocity is 0. That's 2. You didn't have to write that 6 seconds there. I just put that in there to figure stuff out. Right? You didn't have to draw the area into the curve either, but we're just learning. We're learning. We're reviewing. You got to understand this stuff. So this actually hits the ground when the area under this curve equals the area under that curve. That was question 2. This is question 3 from the 2019 APC Mechanics exam, set 2. We got a ball or a sphere at mass m, radius little r, and it's at height h at position p, and it's going to go around loop to loop. This is point A, which is the top of the circle, and they're going to ask some questions. The rotational inertia of a rolling object may be written in terms of its mass and radius as I equals b mr squared, right? So they're coming up with this general relationship that if you got a sphere, the moment of inertia is going to be some variable b times mr squared, where b is a numerical value on the distribution of mass within the rolling object. Students wish to conduct an experiment to determine the value of b for a partially hollowed sphere. The students use a looped track of radius r is much, much bigger than little r. So this one is much, much bigger than that one. So what are they telling us there? That's an important idea. What are they telling us? The fact that this little r of this thing is much smaller than this, what they're saying is it essentially has no size in relation to everything else on this. So we can treat this as a point when it's along the track. Now we can't treat it as a point when we're finding the moment of inertia, but relative to r. So for instance, when this is at this height, when it's up here, its height is just going to be 2r. We're not going to have to subtract the size of the sphere. That's what they're telling us there when they say that r is much, much larger. Big R is much, much larger than little r. The sphere is released from rest at height h above the floor and rolls around a loop. A, derive an expression for the minimum speed of the sphere's center of mass that will allow the sphere to just pass point A without losing contact with the track. All right, they told us something really important there. What just happened? They want the minimum speed, so it just goes around. So they're saying it's in circular motion, but if it was going any less fast, it wouldn't go in circular motion. It would fall off. So, what are they telling us? What is the limiting situation here? We got to think about that. All right. Just without losing, express your answer in terms of B, M, R, and fundamental constants as appropriate. All right. So this has energy to its height. It has no energy due to its motion in the beginning. We got to figure out how much energy is going to need to just get around here. So this is really what's going to drive the problem. It has to be going a certain speed at that point. We got to figure out what that speed is because we know what the position is. its height 2r above the floor, right? So, and then I'm sure we're gonna have to find h. All right, driving. So what's the minimum speed that it needs to be going here? All right, so this looks like a job for Newton's second law of motion, right? This thing's in circular motion at this point. It's going around a circle, and so let's take a look at that. It's it's at the top like that, and here's our object, and it's going around the circle. This is point A, right there. Circle the object of interest, and now what I'm going to look at is I'm going to use my Rtz coordinate system here, and I'm going to go, all right, this is in circular motion. This is the center of the circle. I'm going to make that my r-axis. Here's my object, and if it's just going fast enough to go around a circle, that means the normal force is 0. The only thing accelerating it, and it is accelerating down at this point, is its weight. So this is what the free body diagram would look like. It would be mg down, and let's see, it's going around a circle like this. So this would be the tangential axis. We're not going to use that axis, though. So the free body diagram looks like this. There is no normal force. That's the limiting factor. If it was going much faster, there'd be a large normal force. But there is no normal force here. It's a minimum speed. So sum of the forces in the R equals mass times radial acceleration, right? So we got mg equals mv squared over r, because radial acceleration is v squared over r. It's also omega squared r, but we want speed, so we don't want angular speed in this. All right, so we got that, and want the minimum speed. This is v min. This is v min, right? It's v min because there's no normal force. Mass goes away, and looks like v min to go around is the square root equals the square root of g r. Oh no, that's capital R. Sorry. Not little r. Little r is the radius of the ball. This is the radius of the circle. It's big R, not little r. Oh, sorry about that. That's not right. Let's make that big R. Right, little r is the radius of the little sphere. This is the radius of the circle. That was kind of nice of them to ask that question. They could have just said, what's the maximum height? Suppose the sphere is released from rest at some point P and rolls without slipping. All right? Derive an equation for the minimum height that will allow the sphere to pass point A without losing contact with the track. All right? This is a conservation of energy problem right here. And it looks like mechanical energy is conserved. There's no rolling with slipping. If there was slipping, we would have friction, energy loss due to friction, or thermal energy would increase due to friction. In this case, mechanical energy is conserved. I'm going to call this position 1 and this position A, I guess. Actually, I should call it P and A. So I'm not going to renumber these at all. Energy at P equals the energy at A. All right. I'm going to call gravitational potential energy 0 at the floor. So the energy at P is just gravitational potential energy. We got gravitational potential energy at P because it's not moving. There's no kinetic energy, no work being done between here and here, equals the gravitational potential energy at A, because it does have height at that point. I could have made that the point of 0 gravitational potential energy too, but I know a lot of people would put it there. So let's put it there just so you can see how that would work out. It would probably be easier if I put it here, but let's do this. Plus the kinetic energy, translational kinetic energy at A, plus the rotational kinetic energy at A. mg HP equals mg h at A plus 1/2 mv A squared plus 1/2 I omega A squared. All right, so we're going to need to get rid of omega. So since it's rolling without slipping, which is a key idea, we know that V equals omega R. In that case, it's little r because that's the radius of the little circle, the little sphere. All right, so therefore, the omega equals V over R. All right. Or, and we're going to plug this in because this is going to need to be our speed. That's our speed at A. And that's going to be omega squared is going to be V squared, which is just going to be G big R divided by little r squared. Right? All right. So let's see what we got here. We got mg. I'll bring this over here, and we're going to end up with hp minus ha equals 1/2 mgr, because that's va squared. This is va, right? So va and v min. It's really VA. It's V at position A. MGR plus 1/2. And I is B MR squared. Omega squared is GR over R squared. All right, good. We got our masses can go away. Boom, boom. R squareds can go away. Boom, boom. G can go away. We could do this anywhere. We could do this on the moon. We get the same answer. We're looking for, what are we looking for? We're looking for HP. We're looking for HP. I don't know why I brought that over. Shouldn't have brought that over at all. That wasn't a good move at all. That was a waste of ink. HP. HP is what we're looking for. Equals 1/2 R plus 1/2 BR plus HA. All right. HP equals 1/2 R plus 1/2 BR plus HA. How high is HA? That's 2R. All right. So we got 5/2 R plus 1/2 BR equals H. Maybe I can clean that up a little bit. What do we got? R over 2 times 5 plus B. In terms of B, M, don't need M, and big R. Yep, all right, we're good. R over 2, 5 plus B. All right. And we were looking for a height. That'll be in meters, and that's unitless. And okay, we're good. Good on units. All right. Let's see. All right. Let's erase. All right. The students perform an experiment by determining the minimum height for various other objects of radius r and known values of b. They collect the following data. So they got some spheres of different b's released from different heights. On the grid below, plot the release height h as a function of b Clearly scale and label all axes, including units of and if appropriate, draw a straight line that represents the data. All right, so I did that here. I'll stick it up there somewhere. I'm not going to do it on the board. The students repeat the experiment with the partially hollowed sphere and determine the minimum release to be 1.16 meters. Using the straight line from part C, determine the value of B for the partially hollowed sphere. All right. Well, I used the line just to, and I found that B from the line is 0.8. That's what I got. And then it says calculate the radius of the hoop. The radius of the hoop from all that good information. Oh, that should have been H equals. That should have been H equals. We needed derive an equation. We need an equation. That wasn't an equation before. That's an equation. It wasn't an equation. H equals. All right. So I'm just going to use this this relationship. From my graph, I'll get a value of H. That'll give me a value of B, and then I can calculate R. So let's solve that equation for R. I'm going to take H and multiply it by 2 and divide it by 5 plus B, and that should give me R. Right? Brought the 2 over here, got a 2H, and divided by 5 by B. And then from my graph, 2 times 1.16 meters, I got that 5 plus, and I got 0.80 from my graph, 0.4 meters. So I got R as 0.4 meters. D was, C was the graph. B equals, I got that from the graph. E is R equals 0.4 meters. All right? Got that by taking that relationship and use my value for B to calculate D. In part B, the radius R of the rolling sphere was assumed to be much smaller than the radius R of the hoop. If the radius R of the rolling sphere is not negligible, would the value of the minimum release height be greater, less, or the same? All right, well, let's take a look. Kind of recreated the loop-to-loop. And but now this time we're going to look at this and we're going to say, well, what happens? Here's P. And I tried to measure that so that height is about the same. And what happens if this thing was bigger? I'm going to use red. What happens if our sphere was big? So now it's not negligible size compared to R, right? R was, here's our R. Now that's pretty big compared to R, right? And when it rolls, it's got a radius, it's almost as big as R. So now when it gets to there, it's going to have less energy. A couple things are going to happen. One, they talked about the center of mass. So the radius of the circle that this actually transcribes at its center of mass is actually significantly smaller, right? You know, so this center of mass is really going around a radius like this, which is significantly smaller than that original R. It's also not falling as far. If this had no size to it, you know, that's how far it falls as far as the height difference when we do our conservation of mechanical energy is that, right? But in this case, it's going to actually fall farther, right? Now, in this case, the center of mass goes from here to here, right? So it actually falls farther. Right? It's going to fall farther in this case because it actually ends up lower than if it had no size. It falls farther, so it's going to actually have more energy when it gets to the top here. In order to be going fast enough, we could actually release it from lower. if the radius little r of the rolling sphere is not negligible, would the value of the minimum release height be greater, less, or the same? It would actually be less, right? We don't have to drop it as far to give it enough energy to go around the circle here. It's a smaller circle for one thing, and so it wouldn't have to be going as fast. The circle it's going around. Plus, its center mass is dropping farther. So we could actually drop it from less height. So those are the things I would talk about. That it's when it's bigger like this, its center of mass drops farther at your point P. Plus, your R is smaller here. The radius of the circle is smaller for that big sphere in there. F would be less. All right, there you go. That's the 2019 AP free response set 2. I thought that was harder than set 1. I thought that was more difficult than set 1. The poor students who got set 2 last year. But, you know, they adjust everything anyways. If it's harder, they adjust the scores. So, all right. I'll catch you later.
It's stream. Fair